Hello, my name is Robin. I am a second-year student at Concordia University in Montreal, Quebec, in the Electroacoustic Studies program. In this video, I will briefly discuss and attempt to summarize the concept of dithering in digital audio, and hopefully by the end of it, you will have a better understanding of why or why not to use dither, and if so, which type of dither you might apply to your projects. So, what is dither? Dither is the application of random noise to a digital file in an attempt to randomize and reduce distortion caused by truncation or quantization errors. In order to understand what this means, the first step involves understanding bit depth. Bit depth refers to the number of bits of information within each sample. It's comparable to the audio file's dynamic range, which is the ratio between the smallest and largest values that a certain quantity can assume. 1 bit in an audio file equals 6 dB of dynamic range. So if you look at this graph, these three graphs, they are the same audio file represented with different sample rates and different bit depths. If you have a 44 kilohertz file, 16-bit. What this means is that each of the 44,000 individual samples has 16 bits in which information can be stored. A file that has 44,000 samples, 24 bits, well, each of the 44,000 samples has 24 bits of information that can be stored within. And the 96 kilohertz file will have more than double the amount of samples. However, each sample will still only be able to hold 24 bits of information. So it's important to remember that when you're using dithering, it involves only the bit depth. If you convert your file from 96 to 44 kilohertz, from 44 to 22 kilohertz, you don't need to use dither at all. That's a whole nother process. Dithering involves lowering the file's bit depth from a higher number to a lower number, from 32 bits to 24 bits, from 24 bits to 16 bits. If you look at the three graphs, you will see that the first two, the 44 kilohertz 16-bit and the 44 kilohertz 24-bit, they have the same number of samples on the horizontal axis. However, each of these samples in the 24-bit file can store more data than the 16-bit file. What would happen if you downsample from 24-bit to 16-bit? Well, it will simply truncate parts of the information. A very easy analogy is you have a bottle which contains 24 bits of information, and all of a sudden you have a much smaller bottle which can contain only 16 bits. Well, when you try to transfer from one bottle to the next, it won't be able to contain the same amount of information. So consider a waveform, or any digital file, represented by these amplitude values. Here we have 8 samples that have different values. 1, 2, 3, 4, 5, 6, 7, 8. If we were to take this file, let's say it's in 24 bits, and downsample it to 16 bits, some of the information will be lost. The actual resolution of the file, the bit depth, is reduced, and some information has been truncated. What happens is these numbers are automatically rounded to a new number. So if you look at, for example, the number 8 at the very end, after we lowered the resolution, it became 6.4. However, when it rounds off, it becomes a 6. So your file deviated from the number 8 down to number 6. So the new sequence, instead of 1, 2, 3, 4, 5, 6, 7, 8, has now become 1, 2, 2, 3, 4, 5, 6, 6. That's vastly different from the original file, and this will cause distortion and truncation errors in your file. What dithering does is apply randomness to the rounding of the data through different probability density functions. If we go back to our sequence 1 through 8, and we look at the number 5, which now after lowering the bit depth has become 4. Depending on what type of dither you use, what type of probability density function you use, instead of the number being 4, the possible outcome is now randomized from 4 to 5, 4.1, 4.2, 4.3, etc. If you were to use rectangular probability density function, it is like rolling one die. It is truly random. Any value between 4 and 5 would have the same probability of appearing. Triangular probability density function is similar to rolling two die and taking their sum. With this method, values in the center have a higher probability of appearing. And if your number is in the center, it will round off to the correct number. So the ideal is for the number to be closer to the center in terms of the probability. Gaussian curves take the sum of a large amount of die. It creates a bell curve from the principles of normal distribution, and with this method, the values closer to the center have an even higher probability of appearing. Now, in essence, to explain this, if you take the sequence 1 through 8 and our number 5, which was truncated and has become a 4, if you were to apply these different functions, the rectangular probability function would mean that any number between 4 and 5 could appear. The triangular function means most likely the center number, 4.5, would appear. However, there's still the possibility that any other number could appear. It's just much less. And with the Gaussian curves, there's an even higher chance that the number 4.5 would appear. But there is still the possibility that any other number could appear. So ideally, you want the probability to be as close to the center as possible so that it would round off to the correct number. However, this introduces noise. The noise itself is, depending on the bit depth of your file, sometimes inaudible, sometimes masked by the music itself, and is much preferable to the actual distortion which is caused by truncation. However, be aware that the Gaussian curves or the triangular probability will create more noise than the rectangular probability. So in loose terms, if you're exporting, let's say, one single sound, the sound of a guitar, you might just use the rectangular probability if you're lowering the bit depth. The more complex, the more intricate and spectrally rich your sound is, you might want to use Gaussian curves or triangular probability functions because they are more stable. I have some actual examples so you can visually see in a spectrogram what happens when you use dither or when you don't. This is a sine tone around 320 hertz in 96 kilohertz 32-bit. Now again, dithering only applies when you lower the bit depth, but in this case I also lowered the sample rate. So if we take the original file and I exported it and now converted it to 44 kilohertz 8-bit, you can clearly see these new oscillations and sine tones that appear. Much different than the original 96 32-bit file. These are caused by the fact that the 32 bits of information was now squeezed into an 8-bit container, creating distortion, which you can see. Let's look at the 96 kilohertz 32-bit sound file again, and now I exported it in 44 kilohertz 8-bit, but I used dither, and I particularly used the rectangular dither, because it's only a single sine tone. And here is what the result is. It is pretty much night and day. You have a single sine tone, the original sine tone we had before, with some added noise. However, it is much better to have a single sine tone with some noise, similar to the first one, than a file that has not just one sine tone, but a multitude of new frequencies and oscillations that occur through distortion. It is easily preventable by using dither, and I suggest anyone who works with audio, who will down sample their files, to use dither and to do more research on dither and how it could help you in exporting your sounds. Thank you very much. Thank you for listening. My name is Robin, and I hope you have a great day. Thank you very much.